All right. Our first topic in this first section is going to be one that it should be familiar to you. And so we won't have to spend a great deal of time um, introducing that to you from section 1.1. We're just looking at an intro to linear algebra, and we're looking at the topic that you should be familiar with from your um, previous algebra classes. You probably even teach it: systems of equations. And it turns out that this is what we will explore to a great degree in this course through this entire semester. But we're going to look at it in a much deeper way than probably you've seen in the past. So let's just remind ourselves. Here's a sample system for us. So that's a 2 by 2 system, two equations and two variables. And you should know how to solve those already. If you don't, you might have to do a little review of how to do that. We want to talk about in this short video just some of the key introductory ideas that you're going to want to make sure you understand and carry with you going forward. Now, the first idea is that it is a linear system, and it's linear because all the variables are to the first power. We don't have any x squareds or y squareds or anything like that in here. And we're going to just be dealing with linear systems. Larger than 2 by 2, three equations, three variables, 4 by 4, 5 by 5, and even some oddly shaped ones, but they'll all be linear. And so that's going to be a nice thing to know. Now, you'll remember, if we want to solve this system, the we've introduced several methods of solution. Now, graphing, we can solve some systems by graphing. Graphing serves some other purposes for us, but you need to know how to solve this kind of system by graphing. So you may want to review that. Substitution is also a method of solution for solving systems of equations, but largely it becomes more useful if we're dealing with a nonlinear system, although we can use it on linear systems. The method we're going to be using is elimination, and we're going to use that a great deal, in almost strictly in this course. We'll reflect a little bit on graphing, but elimination is the big one. Now, I'm not going to solve this system for you. You can do that, but you should make sure you just brush up on those methods. And of course, the solution, pretty simple. I'll just give it to you here, is negative 8, 3. All right. Now, what we do want to mention is some things that are going to be unique to linear algebra. So the first one is we'll very often drop the x and y notation in favor of using this type of notation. X sub 1, x sub 2, like that. And so we would have both of our equations written using that notation rather than the x's and the y's. And that allows us to deal with larger systems, 7 by 7 and 8 by 8, big systems. In the real world, the systems that get solved are many hundreds of variables and equations. And so using this kind of subscript notation allows us to keep track of things a lot easier. So just get used to that. Now, there's an idea that we've got to keep track of that we're going to use throughout the semester that we need to make sure we understand quite well. And we're gonna make a lot of decisions based on this idea. And the idea is this, that when we're considering linear systems, we only have a few possible outcomes when it comes to their solution. The system that we just had, that we've got there on the screen, has one solution, negative 8, 3. All right? But when we're dealing with linear systems, there are three things that can happen. We can either have one solution, like the one we've got. We can have systems that have zero solutions, or we can have systems that have an infinite number of solutions. Okay. And those are the only three things that can happen. It doesn't matter if it's a 2x2 system or a 20x20 system. Those are the only three things that can happen. So we there's a lot of importance in understanding that, because we make a lot of decisions based on which one of these things occurs. Now, I mentioned earlier that graphing was not a great method for solving systems of equations. Rather, what graphing does is it's better at telling us why we have the solutions that we do. So for instance, in the one solution case, if we were to graph both of our equations, this is again a 2x2 case, that's why we can graph it on a Cartesian coordinate system. If we were to graph them, we would have two lines that intersect in one spot. In the infinite number of solutions case, when we graph them, we're going to get two lines, of course, but they're going to be parallel. There are no intersections, therefore no solutions. And then finally, in the infinite number of solutions case, we graph one line, and when we graph the other line or graph the other equation, the two graphs overlap perfectly, and so there are an infinite number of intersections. All right? So we understand those ideas pretty well when it comes to 2x2 systems. But these are the same ideas that apply for 3x3 systems. Again, 3x3 systems are going to have 1, 0, or an infinite number of solutions. And graphically speaking, if there's one solution, now, of course, if we're dealing with a 3-variable linear equation, the graph of that in 3 space is a plane. And so a one solution situation would be 3 planes that all intersect in a single point. There's only one way that can happen. The 0 solutions would be the situation where all 3 of the planes do not intersect in any common place. So yes, you could have 3 planes that are parallel, just like pancakes stacked on each other, with a little bit of space in between, and they would have 0 solutions. But there are some other configurations with 3-dimensional planes that would provide us with 0 solutions. Finally, an infinite number of solutions would be the 3-dimensional case of what you see right there, with parallel lines or parallel planes that just overlap each other. And so we can use this graphical method to help us understand why we have 1, 0, or an infinite number of solutions for 2 dimensions and 3 dimensions, but it's also true for 4 dimensions and 5 dimensions and so on, although we would never really be able to graph those things. But we just know that there's going to be 1, 0, and infinite number of solutions. Now, to go along with this, we have some terminology. These systems that have solutions, well, let's start with the one that doesn't, the 0 solution case. That is a situation where we have what we call an inconsistent. So this is inconsistent system. These other two, we'll put it down here, are consistent systems. Okay. And then we could also, this system with one solution, we call an independent solution, or an independent system. Whereas these two systems are both dependent. So we have some kind of overlap in this classification system, but those are some terms you want to become familiar with.